here. 4, 3, 4, 5, and awesome. All right, so did we do 10 yesterday? So go ahead. I want you to try 11 and 12. Before we go on, I want to really just give you a chance to see if you can make whatever necessary changes to the function first. Okay, then get yourself into the derivative for each one. Right, because both of these have a little adjustments that need to be done first. And if you get stuck, that's okay. I'll kind of work through these up here so you can peek when you're ready. But I want to give you a chance to say, all right, I know the power rule. I know what I need to do. I understand this whole constant thing where all I have to do is just multiply 3 by a constant in the derivative. Try 11 and 12 here on page 136. Ooh, that was a big deal. And if you get stuck, ask questions. We're going to have lots of practice with this stuff before I ever actually test you on it. Once we get closer to the end, we'll at least have a couple days of review. I don't know when things are happening, but good job. Anybody need a copy because they don't have one? I got one. Buy a bunch, I'm going to have 2. So 136. Times x to the negative 1/3. But it might just be easier since we have the same variable and we're dividing. Let's just subtract exponents. Okay, so making that switch, and let's just. We would have gotten there the same way if we had rewritten it as multiplication first, right? Calling it x to the negative 1/3, that's equal to. But then when we multiply, we add exponents. Oh my goodness, I'm doing this with algebra 2. Properties of exponents right back there. Kind of weird timing, but there it is. Feels like forever ago, doesn't it? You went from that to this in a year.
It was before the pandemic. Anything before the pandemic feels like.
I know, right? All right, so make that switch and then jump into the derivative. I guess I'll do the first one. Is it? Yep. When it gets warm, I do have like a box fan that I set up. I'm sure. Yeah. Another moment or two as you finish up. But take a look when you're done. For number 12, I went the additional step there in red that I don't think you really have to, but if you do want to make common denominators, just multiply top and bottom by the square root of x and put them together. But I like what's in blue. But what's in red is good to practice too. So if you want to take that extra step, or at least write it down if you hadn't done that, so you have that to look at in the week. What how'd you do? Okay. Still kind of tricky. Not exactly confident yet. Okay, that's okay. We'll keep practicing that. And obviously, like finding the derivative is going to be part of everything that we do. Like basically every problem, like I said yesterday, what's the first thing we should do? Take the derivative. Okay. And so we're going to do that a lot anyway. So I think that'll kind of build your expertise as you go. And these ones are not easy ones for sure. Like something like 11, you know, there's a lot of things to remember and a lot of things to do. So, but if you get what you're supposed to do, if you have a pretty good understanding, I take the exponent, drop it in front, multiply it together, decrease it by 1, and you know sine and cosine derivatives, you'll be in really good shape. Sweet. Okay, cool. So I keep talking about building to this idea of trying to put things all together and use a derivative to find some of those spots. That's what I want to do now. Turn the page. Let's go to 137. We're actually going to go all the way to the bottom of page 137 because it gets us right to the point that I want to get to. And of course, please stop me, ask questions. This is not a sit down and watch me do it and then you try it and then we don't talk about it. We have to really get these ideas out there. So this kind of kicks off the end of this chapter. I know we did it a little bit yesterday, and I want to kind of build on that right now. Determine the values for this function as a horizontal. Okay? And if you were here yesterday, we saw something towards the end of class yesterday where we started to look at a couple of these ideas. And there's really kind of 2 steps to this process. What's the first thing we should do in calculus? Derivative, let's do it. So go ahead. This one's a little bit easier, so hopefully you can find that derivative on your own. Give it a shot. Let's hope this one actually has some answers. But right here is a really good clue to me that there's there are definitely going to be some horizontal tangents because the end behavior of this function is, right? It's even degree, positive leading coefficient, so it has to end up like that. So I have to turn somewhere at least once, right? Maybe a total of 3 times, right? N minus 1 is how many total extrema there could be. That's not amazing. But having that kind of feels pretty good. What'd you get? You can like raise your hand and I can call on you. You know, we can like have a normal class now. There you go. 4x cubed minus 16x. Sweet. Okay, so there's our first step always. When they ask us to find that horizontal tangent or anything kind of related to that idea, let's always start with the derivative, but now what? That's right? And so there's kind of like 2 parts to this, and you can separate it if you want. I'm going to take that derivative, set it equal to 0, and see what we can find. Now, because of that cube, I could find as many as 3 spots. Like I said, it's you know, with a degree 4, so it could turn 3 times. So maybe it is. It could be less though. So what do we do now? Ethan, what do you think? So trying to isolate x, right? Eventually is what we're trying to do. But by moving one of those x's to the other side, now you're kind of splitting them apart on either side of the equal sign. If we can, let's try to keep all of them on just the left, but work on isolating each one. Because let's just see how this plays out, Ethan, so you can see what I'm talking about. Like, let's just let it roll for a second so we can see why this might be a problem. Now what? And the moment that we divide away an x, now we're losing a possible answer. What you're doing is you're dividing away that. And 0 is actually one of those answers. And that's what I don't want to lose. because we know we can't divide by 0, but by dividing away an x, which I think is a good algebraically sound strategy there, right? Let's start getting x by itself, we'll divide it away. We're actually losing the answers. We don't want to do that. But I like the ideas. Connor, I saw a hand. What do you got? The first thing we always want to try to do when solving is any kind of factoring. Okay. And there's going to be a lot of different factoring things that we look for. But I think what you're kind of leading towards is looking for that greatest common factor, right? You found an x that was in common with both. Let's pull that out. But is there a coefficient that we can plot with it just to make our numbers easier? 4. Let's pull out the 4 at the same time. And Ethan, there's that 4x you're talking about, right? There's that 4x. You knew it was there. It was in common, but we just don't want to lose it. So we'll factor it out instead of dividing it away. Now we got 2 terms here, so we're going to have 2 terms left behind. What is left behind when we do that? Factoring that 4x out. X squared minus. Now that we pulled that GCF out, is there more that we can do? Is there something left in what's left inside that's factorable? Yeah, difference of squares, absolutely. So let's call this 3 factors. No surprise there. We could have 3 factors, right? X plus 2x minus. Now, how much work you decide to show from here to get to your answer is totally up to you. I think most of us at this point could probably look at each of these factors and say what the answers are. If you need to do this and set each one equal to 0 and kind of show that algebraic step, go for it. That's what we're going to do. That's kind of what we're doing in this step by saying, oh, okay, x is 0, x is -2, and x is +2. Let's go least to greatest when we write them down. But what's in red there, and even like the blue that's right underneath that, I don't know that you have to show that in calculus. I think we're good enough with our basic algebra stuff. But I'm totally supporting anybody that wants to make sure that they're doing it right, especially if these factors get a little bit more complicated, 3x minus 2, or some unfactorable quadratic, x squared minus 7, something like that. Show as much as you want after that. But the kind of factoring that we can do is, maybe it's that's a D. The difference of 2 squares. Maybe it's just some other kind of quadratic. Maybe it's some difference of perfect cubes. Whatever factoring kind of happens after DCF just kind of depends. Did we do it? Did we find the spots where we think this function has a horizontal tangent? Yeah, right. Determine the values. Remember, when they say values, they're always x values that we're looking for. Let's see how we did. Let's take a look at it. The original function, x to the 4th, what was it, plus 8x squared? Minus, thank you. Minus squared plus 2. I gotta fix my scale. I'm still in unit circle lane. I'm gonna get rid of the calculus if you're cool with that, so we can look at it. Back it up a little bit. There they are. 1, 2, and how would we find the y values? If we wanted to actually let's find the equation of this tangent line or this one or this one. If we wanted to know just more about where those points are, how do we find the -14s and the 2? Now that we know that we've got some x values. Sorry. Into the original. Good. Because what are we going to get if we plug them into the derivative? 0, right? We just solved for them by setting it equal to 0. So we know that those values are going to give us 0 in the derivative. We want to get their actual y values. So you just plug them back into the function. All right, plug in 0. Yeah, I'm going to get 2. Plug in -2, +2. We'll get -2. Nice. Good. That's the problem. Okay, turn the page. I like it. I like it. I want to do this one again with you only because it's got some trig and stuff in there. Let's do 18. Let's do 18 together. And once we do a couple of these, then we can start kind of getting you out on your own and having you try these. But I want to, if we can, start working through some of this stuff together. Very similar question, but again, they're going to restrict any sinusoids down to just unit circle. That's it. And again, 2 pi is not an answer that we can use, right? 0 is, 2 pi is not. That's pretty common. All right, cool. This is calculus A. What should we do first? Find the derivative. Let's do it. Now, is this ready to go, though? Can we find f prime of theta the way that it's written right now? What do we need to do? How can we rewrite this function? Or does that square root initially throw you off? Well, hold on, take a look at it. Is there really anything wrong with the way that this function is written? Don't let a square root or like the existence of a square root throw you off. All I care about are pieces of pi, or pieces of theta, sorry. I'm hungry, I guess. I should have breakfast. Pieces of theta, and whether or not they're written as coefficient x exponent, coefficient theta exponent, or just written as a nice sine or cosine, those are good. I know it's square root of 3, but then it's just theta. And again, theta is just x. In your mind, when you're working through this stuff, this function is actually good to go. All right? So don't let that throw you off a little bit. If it helps, if you want, you can write it in terms of x. That's up to you. You just have to make sure you go back to theta at the end. I don't recommend that because a lot of us might get stuck leaving x at the end and then we lose points. That'd be silly. But if it helps, go for it. So, all right, one piece at a time. The derivative of that. Well, what if it was just 3x? What's the derivative of 3x? Yeah, the coefficient. It's linear. So all I need is a slope. Okay, so what's the coefficient of that? Square root of 3. Yeah. There's the derivative of that first piece, square root of 3. Okay. Now the derivative of 2 cosine theta. Well, what's the derivative of cosine? Negative sign. So what's the derivative of 2 cosine? Negative 2 cosine. Yeah, all you need is the coefficient. That constant that's being multiplied through, just bring that with you and take the derivative of everything else. Nice. Good. Looks a little nasty to start. All right. If they said, hey, find the derivative, then we'd be done. But they're asking us to find all those spots that have a horizontal tangent. So what should we set it equal to? Always. Good. Put the parentheses around the theta if you need them. Don't if you don't. If that was like, theta plus pi over 2, if it had a phase shift or something, then we'd absolutely need them. But even like 2 theta, 5 theta, you don't need it. Cool. All right. Let's solve. What should we do first? Subtract the square root of 3. Sounds good. Okay. Negative root 3 there on the right side. Okay. Now what? Huh? Yeah, this is just a constant being multiplied through. Let's divide that away. Okay. So divide both sides by negative 2. So we get root 3 over 2 because negative divided by negative. And what we're looking for are answers in there. So what are you starting to kind of imagine in your mind or maybe pull out from your notebook as a nice little resource for you in case you don't have this thing figured out. Oh, that was a good one. I'll take that. Nice. It does, yeah, it just looks like some crosshairs. Right? All right, so sine. Is that X or Y values? We want the Y values from the unit circle that have this as their Y values. There and there. What are those two spots? Pi over 3 and 2 pi over 3. There they are. Done. Okay, so it's all about isolating sine and cosine, and just using the unit circle. Or using inverse trig. I mean, you can jump into a calculator and say, all right, what's the inverse sine of radical 3 over 2? Make sure you're in degrees, so you recognize 60. And then it's not only going to give you 60, though. Remember, because when the calculator goes looking for answers, when you do inverse trig, it looks like that. Right? It opens up a positive and negative angle, and as soon as it gets an answer, it stops. And it's going to give you one. It's never, ever going to get to there. Calculator's never going to get you. But we know that if we're not at some quadrantal spot, right, we're not at 90, 180, 270, or 360, there's going to be two answers. If it's just sine and cosine. It's going to be 4 answers if it's sine squared or cosine squared. Because you got the positive and negative version. Right, all those reference angles and all those duplicates all come in. Cool. All right, so I wanted to kind of have us walk through that a little bit so that you can get a little bit more comfortable with these ideas. All right, let's. Yeah, lots of time. I like this. All right, next page. Next page. I'm skipping the next one. Going to page 139. And now that we've done enough, I think we can almost like recreate this chart that'll be a perfect kind of wrap up of what chapter 2 is going to be. Because what we need to start doing is recognizing those connections between the derivative and the function in both directions. We're going to work both ways for sure. Like, here's a function, tell me about the derivative. Here's the derivative, tell me about the function. And that's this one. Here's the derivative, tell me about the function. So if the derivative is 0, and I don't know why they capitalize F there. I don't know what the purpose in that is. But if the derivative is 0, what do we know about f of x? And I think they're saying, okay, like here is like one spot, like here's an x or 2 or 3 or 4 or however many there are. And when you plug those x's in, you get 0. What do we know guaranteed about the function at each of those spots? Good. Then f of x has a horizontal. And like in my mind, I'm starting to not even like draw those tangent lines out anymore. It's really this feeling that like the function stops increasing or decreasing. It just flattens out for a brief moment, or it could be a while. But usually we look at functions that are like, it's just like a moment in time where things stop going up. Cool. Rate of change is 0, right? I'm walking across this floor. I'm not going up or down. I'm walking across that horizontal tangent. Okay, but what about if the derivative is positive, greater than 0? Then the function, now looking like a whole section of this graph, where the derivative is positive everywhere. What do we know about the graph at that spot? Yeah, positive slope increasing. I like increasing even better. I want to talk about the behavior of the function. Then f of x is increasing. I think the more we start talking about like the actual function of what it's doing, rather than talking rather than talking about like what I could draw on the function to talk about it, I think that'll help us out even more. Good. It's increasing. Okay, what about if it's this one gets easier? If it's negative. Yeah, it's going down. Decreasing. And of course, we're always talking left to right. We always read graphs from left to right. that was kind of what we got to for a little while. And now what they're going to start doing is saying, all right, well, let's talk about when we see a change in a very specific way, when the derivative changes. So think about like a section of a graph, and you're kind of watching the derivative change. And the derivative goes from positive to negative. Yeah. Yeah, perfect. Then f of x has, I'm going to look at the changing below, has a relative maximum. Has relative maximum. Guaranteed. And there's nothing that I could do to draw a graph that goes from increasing to decreasing without hitting a relative. And so what does that mean then from going from negative, so decreasing, to positive? Has to be a minimum. Has to be. Now, I don't know if it's going to be a global or a relative, but I can guarantee it's going to be a relative. Has a relative. Nice. Good. Okay. And now that we have that, now we can really start putting the pieces of things together without even looking at graphs. Now, I know there is a graph there below, and I want to see if we can try it. They give us the graph of a function. Okay, so this is a function. This is actually one that we've seen before. But what I want to try to do is figure out if we can draw a possible, and this is just a sketch, it's not going to be perfect, but try to draw a possible version of what the derivative might be along the way. And the thing that I think is going to make this easier, we don't try to do it all at once, but we just kind of go point by point by point. And then we'll just connect things in between. Kind of like we've done always. When we sketch graphs, we label some important points and then we do our best to connect. And so they didn't mark up the scale. 1, 2, 3, 4, 5, 6, -7. What do you think the derivative might be at that point? Your best estimate to what the derivative is. 3? Anybody else have another? 4? Here's the only thing about 3, Jazz, that I'd be careful of. If we actually did draw a tangent line here that had a slope of 3, I would go up 1, 2, 3, and over 1, and I would actually hit the graph again. And that's what I want to try to avoid. Remember, derivative is just the slope of the tangent line at that spot. And I want to try to pick one. I think 4 looks pretty good. That if I, it's not great. Could even be 5. 4 is pretty good, though. We'll go 4. Like, once I make that guess, I want to test it out. I want to look at it and say, okay, well, let me go that far. Let me go up 3 and over 1. And like, do I hit the function? Am I just missing it? Because that's kind of what I'm hoping for, is that I'm just missing it. I like that. 4 looks pretty good. I'll leave that up. All right, so now go to -7. If we're picking 4 as the value of the derivative there, when you go to -7, where's the point going to be? At 4, that's the whole point. The output, your y values, when you draw the graph of the derivative, is the slope of the tangent line from the function at the top. Nice. Okay. Probably -6. Okay. What do you think? What might the derivative be at that next point when x is -6? What's a decent guess? 2? Yeah, all right, let's test it out. Let's actually go up 1 over 2 and try to like connect that point with this one and see if that looks pretty good. Yeah, I like it. That's good. So -6, 2. And what we start to see as we build the derivative is that as these points, like those 2 points right there, you know, the next one gets lower, right? 4 went down to 2. Is that the slope of my tangent lines are starting to flatten out. They're becoming less steep. My rate of change on my function is decreasing. I'm not going up as fast, right? If I'm walking up this hill, I have to work really hard at that point right there. I don't have to work as hard to get up the hill at that point. All right, next one at -4. What's the slope of that tangent line? Absolutely. It's a relative extremum. When I'm at a relative extremum, I know guaranteed I've got a slope of 0. And so all of your x values on your derivative graph that hit the x-axis, those are all of your horizontal tangents. Okay, what about at -2? What is that slope? What do you think? Huh? -1, there you go, yeah. So -2, -1. And so now that I'm dipping below the x-axis and into the negative y values for the derivative, now I know that the function's decreasing. And seeing that change from positive to negative at -4, oh, okay, that's, look at the chart above. We just went from positive to negative, got to be relative. Okay, what about at -1? Now this is hard to draw the tangent line because there's actually a lot of tangent lines, I think. Like there's a lot of lines that I can draw that only hit the graph once in the nearby space, right? But only one of those can actually represent the derivative. And that's why I want you to start. I know we start like, oh, derivative is slope of the tangent line. What I want you to start thinking about is what direction the function is moving at that point, right? We're going down. When I get to -1, and I'm probably pointed down steeper than I ever have been at this point in the function. And so when I want to think about like what that tangent line could look like, it's really about what direction the function is going. What is the rate of change at that spot? If I'm on a pair of skis, how fast am I going if I point those things down? Pretty darn fast, right? That's why I snowboard blues, not blacks. So what do you think? What do you think that slope might be? -3? Let's test it out by going down 3 and over 1. Look, not bad. We could try another one. We could try -2 and maybe see if that fits a little bit better. Ugh. I just hit that point by doing -2, so I don't think that's steep enough. I think we're better with -3, and so let's go for it. Again, we can't be perfect, and that's okay. We don't have to. So -1, -. All right, what about at 1? 0. Back up we go. Now, it's a little frustrating that they didn't really include many points in between there, right? Because we go from -1 to -3, and then all of a sudden we're back to 0 again. But hopefully what you can see is that because we're starting to flatten out, like the slopes of these tangent lines, they're going to get less steep, which means that the derivative is going to kind of creep its way back up. -2, -1, and then kind of back to 0. All right, see if you can do the last one. There are 3 more points, one at 3. There's a 3 right there, one at 5, and one at 7. Do your best to estimate the derivative. And then, but don't connect it yet. We'll connect it together. 5 somehow. Those are my guesses. I got a new lamp that's working, and look how happy this boy is. Even right there under that lamp. Right? Yeah. It's not super warm. I also got like a timer for 12 hours a day left. So what do you think? Maybe 3. I put a 2. I thought that was pretty good. It's not an exact science, of course. That's why we have limits with the whole derivative thing, so we can do that. But I don't know, like again, it's a hard one to draw because it kind of like crosses through. Maybe even 3. Did anybody put 3? 3 is good. I think 2 or 3 is good. Did anybody put anything else besides 2 or 3? 5. It looks really steep. Yeah. I think something at least 2, but probably no more than 5. Because if you went 5, 1, 2, 3, 4, 5, and over, I think that looks really good. I'm good with that. I'm happy with that. Let's split the difference. We'll do 3 because a couple people put some 2s and some 3s. And so I'll go with the 3. That looks good. 5, everybody got 0, right? Nice relative extrema there. And then for 7, I put -5. I felt it was pretty steep at that point, and I tried to draw it out as best I could. I went 1, 2, where'd I go? 1, 2, 3, 4, 5, and over. Yeah, that just felt pretty good right there at -5. Now, I think the tricky part about this now is like, how do I know how to connect? How do I draw this thing in a way that, like, oh gosh, I look at that and I don't see, like, I mean, it kind of looks like quadratic here maybe, and I can see it like kind of like coming down like this, but like, what am I supposed to do in there to connect kind of all that weird space? Because I kind of left out some important points, I think, right? Leaving out 0 was a big one. Because if we had put 0, I don't know, maybe like -1, something like that, -1.5, maybe -2, something like that. I think that would help a lot. And so what do you think? Well, first of all, what type of function do you think f of x is? To the 4th, yeah, nice. -x to the 4th, probably, something like that. Okay, so that's a pretty specific one. So more in general, what type of function is -x to the 4th? And I don't know how long it's been since we've actually tried to draw these out, but what do we know about the general kind of graphical descriptions that we use when we talk about polynomials? What do we know about polynomials in terms of what they look like visually? Oh, sorry, Jazz, you said? They're continuous. Good. Every polynomial is continuous. Now, that doesn't mean necessarily the derivative is. It is possible that we find some spots where the derivative doesn't exist. Okay? Now, we haven't looked at them yet, but drawing something, even ever so briefly, that has a vertical tangent line. We haven't looked at that yet. I can draw a graph that's continuous that at a spot, only for a second is going straight up. What is the slope of a vertical line? Not infinite. It's undefined, same kind of idea. But either way, it's not a number, right? So the derivative doesn't have to be defined everywhere, even if the function is. But I don't see any of those spots here, so that's good. I heard somebody else say something. So you said continuous. Did you say something? Smooth. Okay, what do you mean by smooth? So there's a flow to it. There's no sharp turns and absolute values, like kind of edges to it. We want to try to draw it as smoothly, as rounded, and if possible, as continuous as we can. So when you try to connect this, I think you kind of said it. You want to have some flow, like some natural, like almost like cascading, like water eroded smoothness to it. For all my people out there that dig that kind of stuff. So when I try to draw this thing out, hopefully I can erase this, but like I'm not gonna do that. I want to try to avoid that sharp turn like that. Please undo yourself. Yes, okay, good. I want to try to find some roundedness, some smoothness, and say, all right, if I get to there, and I know I gotta make my way down like that, I want to get rounded at that spot as best I can. But even like then I still have to make my way back up too, right? If that's probably my steepest point, I want to have that kind of turn want to have this turn. I want to get myself to a point where there is continuity if I can, if it works. Again, vertical tangent lines are going to cause us some issues later on. Any chance I get, I want to make sure that I'm nice and round. So what do we do here? What are we going to do to deal with the fact that this graph doesn't just stop at those points? If the graph keeps going, then the derivative will as well. Let's do the left edge first. That arrow that I know is pointing down and to the left. But remember, we read this graph in this direction. What is happening in that little red section right there? Is the graph going up or down or what? I heard two answers. Smile. Left to right, we're going up. Right? Now I know the arrow, like I said, I know the arrow's pointing down on the left, but as we read this graph from left to right, this thing is going up. Now, is it going up quickly or slowly or really, really fast? And probably only gets faster as we go this way. Right? As we head down towards the left, and then we read it from left to right, this graph is probably increasing really, really quick. Okay, same thing on the right here, right? This section over here, now that one's easier to read because we actually are going from left to right. But as that graph continues down in that direction, we're looking at x to the fourth, right? Sven said it really well. This is probably like an x to the fourth kind of graph, a negative x to the fourth. And as these numbers get bigger, x to the fourth takes big time control over all the action. And these numbers are going to either increase or decrease really, really, really quickly. So what does that mean then if the left side of this graph is increasing very quickly? What does that mean then for like the left edge of my derivative? If the graph is increasing a lot, what kind of numbers are we expecting for f prime if the graph is increasing quickly? Really big numbers in which direction? The positive. What about on the right? Graph is going down really fast. What kind of numbers are we going to get? Really big negative numbers. Nice. Now, Sven said that this one was x to the fourth. Could it be x to the sixth? Negative x to the sixth, or negative x to the eighth, or negative x to the 10th? Probably, right? Now, we'd probably see like more action, you know, maybe some flexing or some flattening out or something like that if it was a higher degree. But even for sure, right? What about the degree of f prime of x? If your arrows are going in opposite directions, what do we know definitely about the degree? I don't know if it's got to be odd. Does that make sense if the degree of the function's even, but the degree of the derivative is odd? Why? Always, 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 always good, right? We're always going to take one away from the degree. Because if we're doing each one, right, we're just doing term by term by term, the biggest power is just going to go down by one. So cool to kind of expect that. Man, we are flying. I wasn't even sure we'd get to this page yet. I love it. Turn the page. Let's finish up just these last couple of minutes. We will not finish this page right now. But I want to work on the left-hand side first. The left-hand column only, okay? Because that's the same exact graph that we're looking at right now, okay? And if you look at all those questions there on the left-hand side, they're all going back to looking at the graph, but look at the word at the top of that graph. Pictured below is the graph of the function f of x. Answer the questions that follow about f prime. Now, how about this? Take a look at the page next, the graph next. We got two columns there. We got one on the left, one on the right. Pictured below is the graph of f prime of x, different graph. So consider these separately. These are not related to one another. Answer the following questions about f. Right, and I know that we just took a while to draw basically like our first real try at the derivative. Now we have to look at this graph and say, okay, I'm not looking at the function. I'm looking at the derivative. And the things that matter to me, positive versus negative versus zero, not increasing versus decreasing, because that's the conversation that we'll have after. But you know what? That was a good long day. I'm good there. Let's take these last 2 minutes. We can decompress. You guys worked hard today. I know you got 5, 6, 7 classes a day, so I want to give you a chance in between to relax. This seems like a good stopping point. Plus, I never get as far in 4th period as I do in 2nd. I mean, obviously, look at you guys. So I'm good. You guys can rest and relax. We'll get after page 140 tomorrow. Thanks, everybody.